Okay, hello everyone. In a new video. On this one we are going to solve an exercise related to mechanics in the chapter of pressure in liquids. This exercise was a previous one in the brevet exams in 2011 second session, third exercise. The title of this exercise is Determination of the Density of a Liquid. Given atmospheric pressure P atmosphere is equal to 76 centimeter, and here we must be very careful. So notice that here the quantity is the pressure and the unit is centimeter. So notice that the pressure and the unit, so the quantity and the unit are not in agreement, because we know that the unit of pressure is either Pascal in the SI or in Newton per meter square. So from the early beginning we must write the given correctly. So here, because the unit is given by centimeter, so the value, this value 76 centimeter, correspond to the depth or the height corresponding for the atmospheric height. So the atmospheric height here is given by 76 centimeters. Moreover, knowing that centimeter is not the SI unit of length or depth, so in order to convert from centimeters to meter, we simply divide by 100. Then 76 divided by 100. Then the atmospheric height or depth is given by 0.76 meters. And the density of mercury, rho Hg, is given by 13.6 gram per centimeter cube. So the density of mercury, Hg for mercury, is given by 13.6 gram per centimeter cube. And knowing that the gram per centimeter cube is not the SI unit of density, in order to convert from gram per centimeter cube to kilogram per meter cube, we simply multiply by 1000, then 13.6 multiplied by 1000, then the density of mercury in the SI is given by 13,600 after plugging this on the calculator, kilogram per meter cube. And the density of water is given by 1 gram per centimeter cube, so also this density is not given in the SI, then 1 multiplied by 1000, then the unit of density of water in the SI is given by 1000 kilogram per meter cube. And G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Number 1, atmospheric pressure. Part 1. We consider a U-tube containing water at equilibrium, figure 1, so they mentioned this figure, now we can use it. Notice that till this moment they didn't mention anything about figure 2, so we are not allowed to use it. Now, number 1, the 2 points A and B are submitted to the same pressure, which is the atmospheric pressure. So notice that the point A and B are at the free surface of water. So whenever we are interested in pressure, we always look upward. So looking upward, there's nothing found above the points A and B, so they are submitted to the atmospheric pressure. Now, calculate in Pascal the value of this pressure. So we are interested in number 1, calculating the atmospheric pressure. We know that the atmospheric pressure is equal to the pressure exerted by 76 centimeter column height of mercury, and the pressure is given by the density of the liquid. Here the density, the liquid we are using is mercury, multiplied by the value of G, multiplied by the depth, which is given the atmospheric height. Now the value of the density of mercury is given by 13,600, and the value of G is given by 10. The atmospheric height is given by 0.76. Plugging this on the calculator, then the value of the atmospheric pressure is given by 360. Since everything is expressed in the SI, so the value of the pressure will be in the SI, which is in Newton per meter square. Notice that here they are telling me calculate in Pascal, so another unit for Newton per meter square is given by Pascal. So the value of the atmospheric pressure is given by 103,360 Pascal. And let's write here in the given that the atmospheric pressure is given by 103,360 Pascal. Now in number 2, the 2 points A and B are in the same horizontal plane, justify. So we always answer this type of question using the rule of 3, and it's given by same liquid, at equilibrium, and either same pressure or same horizontal level. So since they are asking us why they are in the same horizontal plane, so we will eliminate this. Our answer will be since the both points A and B are in the same liquid at equilibrium and submitted to the same pressure, and here the same pressure is the atmospheric pressure. Then let's say A and B, or since A and B are in the same liquid, comma, so this is the first idea. Second idea is given by at equilibrium, and submitted to the atmospheric pressure. Then for this, then A and B are in the same horizontal level, or let's say the same horizontal plane or level is the same, are in the same horizontal plane. Now, number 2, density of liquid in one of the two branches of the same U-tube. So these are the two branches of the U-tube. We pour a quantity of a liquid immiscible with water of density rho. So immiscible means it doesn't mix with water. Now at equilibrium, the height of the liquid is h is equal to 20 centimeters. So knowing that centimeter is not the SI unit of length, in order to convert from centimeters to meter, we simply divide by 100. Then 20 divided by 100. Then this height is given by 0.2 meters. Let me make some space here. And that of water above the surface of separation of the two liquids is h1 is equal to 16 centimeters. Knowing that centimeters is not a unit of length, so 16 divided by 100. Then the depth h1 or the height h1 is given by 0.16 meter. And they mentioned figure 2, now we are allowed to use it. So here what's happening that we have poured, this is water. And we have poured in the branch A, so one of the two branches, this is the branch A, a quantity of liquid immiscible with water. So this is the quantity of the liquid. So this is the liquid L, this is water, and this is the liquid which is unknown of density rho, knowing that we are interested in determining the density of this liquid. So the height of this liquid is given by h, the value of h is given by 0.2 meters. And above the point D, the level of water rises to a height given by h1 is equal to 0.16 meters. So this is the given, and everything is at equilibrium. Now part 2, we are in part 2, number 1. Determine in terms of rho the pressure at the point C. So first let's check to which pressures the point C is being submitted. So always whenever we are interested in determining the pressure, we always look upward. So the point C is submitted to the pressure of this liquid and to the pressure at the point A, which is the atmospheric pressure. So here, because they are telling us the pressure at the point C, so they mean the total pressure. So always before determining the pressure at the point, we need to mention to which pressure this point is being submitted. Then let's say C is submitted to the pressure of the liquid and to the atmospheric pressure. So usually they give half a mark for this statement. Now we are ready to determine the pressure at the point C. So the pressure at the point C from this is it is the pressure due to the liquid. So let's denote this pressure by PL plus the atmospheric pressure. And we know that the pressure of a liquid is given by the density of the liquid times G times the depth or the height of this liquid. So it's given by, now the density of the liquid here is denoted by rho, multiplied by the value of G, which is G, and multiplied by the depth, which is denoted by H, plus the atmospheric pressure. Now notice that here, since they are telling me in terms of rho, so we must keep rho as a variable, knowing that we are determining PC. So this is equal to, now keeping rho as a variable, the value of G is given by 10, and the value of H is given by 0.2, plus the atmospheric pressure. The value of the atmospheric pressure is given by 103,360. Now multiplying 0.2 by 10, so this gives us 2 multiplied by rho, plus 103,360. So the pressure at the points is given by 2 rho plus so notice that for this number I didn't include any unit, so it's better whenever we have determined a quantity in terms of another quantity, it's better not to include any unit. So here let me write that PC is equal to 2 rho plus 60. And now in number 2 they are telling me to calculate the pressure at the point D. So here, because they didn't tell me in terms of anything, we need to give a numerical value for the pressure at the point D. Now referring to the point D, so always whenever we are calculating or determining pressure, we always look upward. So the point D is submitted to the pressure of this liquid, which is given by water, and to the pressure of the point B, which is the atmospheric pressure. Now let's say D is submitted to the pressure of water and to the atmospheric pressure. So they usually give a half a mark for this statement. So now let's calculate the pressure at the point D, which is denoted by PD. It is equal to the pressure exerted by water, so let's say PW, plus the pressure due to the atmosphere, which is P atmosphere. Now the pressure due to water, because it's the pressure due to liquid, and it's given by the density of the liquid times G times H. Now the density of this liquid, what does this liquid represent? It represents the water, so the density of water is denoted by rho W multiplied by G multiplied by the depth at this point, which is given by H1, plus P atmosphere. Now the value of the density of water is given by 1000, the value of G is given by 10, and the value of H1 is given by 0.16, plus the value of the atmospheric pressure that we have already calculated, which is given by 103,360. So plugging this on the calculator, it will give us 1600 plus 103,360. Now plugging this on the calculator, Then the value of the pressure at the point B at the point D is given by 104,960. Since both of these quantities are expressed in the SI, so the value of PD will be in the SI, which is Newton per meter square. And we know that another unit for the pressure, or Newton per meter square, is given by Pascal. So the pressure at the point D is given by 104,960 Pascal. So here let me write that the pressure at the point D is given by 104,960 Pascal. And now in number 3, the pressure at C and the pressure at D are equal, so they are giving me the result, but they are asking me for the justification. So always such type of questions. So this is the point C and this is the point D. They are asking me why they have the same pressure. So always such type of questions are answered using the rule of 3. So either we need to say same liquid at equilibrium, and either same pressure or same horizontal level. So since they are telling me why they have the same pressure, so we will eliminate this, and our answer will be the same liquid at equilibrium having and in the same horizontal level. And this is indeed true, because here if we refer to this figure, we can see that they are at this U-tube is being at equilibrium and they are in the same horizontal level. Now as for the liquid, the point D is in water. However, the point C, above the point C we have this liquid, and below the point C we have water. But whenever we need to determine whether this point is in which liquid, we always look downward. So whenever we are calculating pressure, we look upward, but whenever we need to determine whether this point is in this liquid or in this liquid, we always look downward. So indeed the point C is in water, which means that the point C and the point D are in the same liquid. Then let's say since C and D are in water, which is the same liquid, comma, at equilibrium, and in the same horizontal level, then C and D are submitted to the same pressure. So now we can say that the pressure at the point C is equal to the pressure at the point D. Now in number 4, they are telling us deduce the value of rho. What does rho represent? It's the density of this liquid, and by deduce it means that we need to use the previous part. In the previous part, we have determined a relation between the points between the pressures at the point C and D. So we are in number 4. For sure we need to use this equality in order to determine the value of rho, knowing that the pressure at the point C is given by 2 rho plus 103,360, which is equal to the pressure of the point at the point D, and its numerical value is given by 104,960. Knowing that we are interested in determining the value of rho, so what's the type of this equation? This is a linear equation and one unknown. The unknown is rho. How do we solve this equation? We put rho on one side and all the other numbers on the other side. So dragging this number to the right hand side, it will gain a minus sign. Then 2 rho is equal to 104,960 minus 103,360. Then the value of 2 rho is given by, after plugging this on the calculator, is given by 1,600. I will continue this part here. So we have now that 2 rho is equal to 1,600. Knowing that we didn't determine the value of rho, we determined the value of 2 rho. So dividing both sides by 2, then the value of rho is equal to this fraction. Plugging this fraction on the calculator, now it's given by 800. Since everything is in the SI, so the value of rho will be in the SI, which is kilogram per meter cube. Then the value of this liquid, which is immiscible with water, is given by 800 kilogram per meter cube. And let me say the following. Notice that this liquid is floating on the surface of water, and this is reasonable. Our answer is reasonable. Why? Because the density of water is given by 1000 kilogram per meter cube. In order for this liquid to float on the surface of water, it must have a density which is less than 1000 kilogram per meter cube. And according to our calculation, the value of rho is given by 800 kilogram per meter cube. And indeed, the density of this liquid, which is immiscible with water, is less than the density of water, which is given by 1000 kilogram per meter cube. And by this, we have finished solving this exercise. I hope it was beneficial for you guys out there watching it, and see you soon in a new one.